So my name is Mark West, and my Twitter handle is in the bottom right-hand corner of all the slides. And if you want to download my slides after the talk, you can just follow me on Twitter or just look at my handle on Twitter, and then you can get hold of the slides. So I'm going to be giving you a practical-ish introduction to data science this morning. And the reason I call it practical-ish is because with data science, it's really fun to get hands-on straight away, right? Just download the stuff and start hacking away. But the message that I want to put across today is to get real value out of data science, you need to understand some of the theory. So I'm going to be talking about the theory to start with, and then I'll have a practical section at the end. My talk, first about who am I? Well, you've just seen the introduction video. So I'm actually a Java and developer architect by trade. But for the last couple of years, I've been managing a team of data scientists at Bouvet in Oslo. And in my spare time, I lead Java Bin, the Norwegian Java user group. So the talk looks like this. I'm going to start with what is data science. I'm going to explain what data science is, talk about the competencies, the kind of teams you need, the roles you need to work with data science. Then I'm going to move over and talk about some very simple machine learning algorithms. The reason I'm going to talk about this is I want to put across the message that machine learning is more than deep learning. It's more than neural networks. It's also about simple applied statistics. So I'm going to look at some simple machine learning algorithms that data scientists often use, and then I'm going to wind everything up with a practical example, and hopefully I'll be finished by 10 o'clock so you can all get a coffee before the next talk starts. So let's get started. What is data science? Well, when you want to know what something is, what do? You go to Wikipedia, right? And I have this lovely quote here from Wikipedia saying that data science is basically an interdisciplinary field of scientific methods, processes, and systems to extract knowledge or insight from data. Brilliant, right? It's a lovely quote, but what does it mean? All right, let's delve into this quote a little bit. Let's start with the word interdisciplinary. What does that actually mean? Well, if you think about data science, you need to be able to program. You need to be able to write good code. You also need to understand the domain you're working with. But if you just work with computer science and domain knowledge, then you're basically doing software development. To really work with data science and get value out of it, you need to understand the underlying mathematics and statistics that data science or machine learning algorithms are built upon. And this person in the middle who can do all of these, they're pretty difficult to get hold of, right? But they are available. And I do really think that computer science skills are very important for data science because I've met a lot of data scientists who can't write good code. So when they're finished writing their code, it has to be delivered to a developer to translate it into something that can be put into production. And that, I think, is a problem. So I would say that a data scientist really needs to be good at all of these things here. If we look at the next part of the quote or the definition of data science I want to look at, that data science is scientific. Well, that's because data science is often research-based, or even based on a scientific method, based on hypotheses. Because with general normal system development, you know what you're going to build, right? A Java application, you're going to have some kind of application server on the bottom, you're going to have Hibernate, Spring, all that kind of stuff. But with data science, you have no idea if the project you're embarking on is actually going to succeed or not. So often, the data science process starts with a question or a hypothesis, or something that you want to prove or disprove. And then when you have that question, then you start gathering the data. And this takes ages because you have to go to all the grumpy people who own the data and say, can I have your data? And they're like, why? Why should I give you my data? This takes ages. When you finally have that data in place, then you can start messing around with it and applying simple statistic methods and also some machine learning to your data to try and work out how it hangs together. Are there holes in your data? Is there correlations in your data? These first three steps here are actually 60 to 80% of the job, I would argue, when working with data science. When you're at the point where you understand your data, you're finished with step 3, then you can actually start modeling. You can choose an algorithm or way that you want to work with your data and apply it. But then the output you get from that might not actually be very understandable, so you have to interpret it and work out what it's trying to tell you. And then you have to go to your boss who knows nothing about data science or applied statistics and explain to them what you've done in a way that they can understand. And then finally you finish. Now, this process here, I've drawn it up as a sequential process, but it's actually iterative, right? Because, you can get to step 3 and realize, hey, I need more data. Or you can get to step 3 and realize, we can't answer this question, it's too generic. So the whole process here is meant to be iterative. But there's something missing here. How do you get the bloody thing into production? And that's often a question that isn't answered by machine learning evangelists. But the thing is, you have to get your code into production. You have to run it in prod. You have to operationalize it, you know? And that's where you need different roles in your data science project, because you have your data scientist, who's your kind of mad scientist who's like pulling in data and messing around with it and doing all the cool stuff. But you're going to need somebody to put it into prod. You're going to need somebody who gets hold of the data and makes it available for the data scientist. That's your data engineer. And not only that, you need somebody, I've actually written data visualization here, but it's more communication. You need somebody who can get the results of the data science and actually make it understandable. You know, middle managers don't want to look at a big Excel sheet full of numbers. They want to see an infographic that explains everything in one picture. And that's where the data visualization comes in. And of course, you're going to need a process owner, not a project manager, but a process owner, because they're the person who's running the project, of course, but they're managing the stakeholders, saying to them, okay, data science takes time, so they have to understand the data science process. They have to keep the team aligned in the same direction, you know, and they have to go around the organization and evangelize the team, what the team's doing. So there are different roles here. And it doesn't mean you need 4 different people in every data science project, but you need to cover these roles in your data science team. So going back to the Wikipedia quote, data science is about extracting knowledge. Okay, what does that mean? Does it mean that data science is just business intelligence with a new wrapping? I mean, it's a fair question, right? I would argue no, a big no. I would say that data science, if anything, is an evolution of BI. It's the next step. BI has a place, but data science gives us access to new methodologies, new techniques, where we can take business intelligence to the next level. So some examples of where data science builds on business intelligence. One is like data sources. You know, business intelligence traditionally is about, you know, schema on write. You take your data and you apply it to some kind of structured format. But like data science allows you to work with unstructured data. Business intelligence often uses data visualization statistics. Data science uses those, but it also adds the ability to work with things like machine learning. And then the goals of business intelligence are often about strategic decision-making, steering the ship based on what happened last month. Whereas data science, through the use of machine learning, gives you access to cool new functionality, you know, like self-driving cars or image or facial recognition or textual analysis. So very important, you know, I think that the boundary between data science and BI is moving, and it's becoming fuzzier and fuzzier as well. So like, if you're working with BI, it doesn't mean you don't work with data science, and the opposite as well. So while we're talking about machine learning, there's a lot of rubbish out there about machine learning. People get confused. Everybody talks about AI, because it's the cool phrase. This is just a marketing term. AI, for me, is really, really broad. It's about getting computers to be like us. And AI has as much to do with philosophy, you know, what is intelligence and psychology and linguistics, as it has to do with technology. I would argue that what we're doing in industry, we're working with machine learning. We're basically using applied statistics to, you know, get value out of our data. And then, of course, you have deep learning, which is the really cool thing that I'm going to be talking about later on at 11:20 today. And deep learning is basically neural networks, black box learning. I'm not going to talk about deep learning in this talk. I'm going to talk about more simple machine learning algorithms. So I'm at the end of the first part of the talk now. So just to sum up what I've said so far, data scientists require math and statistics skills in addition to domain knowledge and traditional software development skills. Data science is hypothesis-driven. It's more research than like, you know, building something, because you don't know what you're going to get when you start building it. Data science projects require a range of competencies and roles. And, you know, as I mentioned before, you don't need 4 people, a data engineer, data scientist, visualization, and process owner for every project. You can have one person that does more than one of these roles, but these roles need to be filled. And data science can be seen as an evolution of business intelligence, providing additional capabilities through cutting-edge technologies like machine learning and unstructured data. On to machine learning algorithms. Let's talk about some machine learning algorithms. Now, machine learning, as I mentioned before, is basically a field of study that gives computers the ability to learn without being programmed. So basically it's an inversion of control. If you look at the boxes on the right-hand side of the screen, traditional programming is about a software engineer sitting with a bunch of data, they understand the business, and they're going to apply some rules to the data to get some kind of output. Whereas machine learning, what you do is you take that output and you put it into the computer along with new data, and you say, okay, I want you to find the correlation between this data and traditional output so we can maybe make some kind of predictive model. And when we're working with machine learning, one thing to remember is that we're actually looking for generalized models in most cases. So imagine you go back to work after this conference and your boss says to you, okay, you've been to the big data conference and I want you to give me some value now. I want you to create a model that can find faces in pictures. So what do? You get loads of training data, loads of faces, and you feed it into your algorithm or your model. And what you want your model to do, you want it to basically come up with an internal representation that looks something like this. A generic face, mouth, nose, eyes. Okay, that's what a face looks like. What happens often is you end up with an underfitted model. That's when your training data isn't very good enough, or you don't have enough of it, or you don't allow your model time to learn the correlation between a picture and what a face is. So that often happens. The other side of the scale is overfitting. And I have to put a trump in there, I'm sorry. But anyway, overfitted model is when your algorithm or your model has memorized the training data. So it will recognize all the faces that you've shown it before, but when you show it new faces, it won't see them because it's memorized the training data. So overfitting is something we often want to avoid, and I'm going to come to an example of that later on in the talk. So machine learning types, there's different types of machine learning out there. You have supervised learning, which is about building predictive models based on historical data. So an example of supervised learning is the facial recognition thing I showed you just now. You show an algorithm or model lots of pictures of faces and say face, 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 and eventually it will learn the link between a picture of a face and a face. So that's about predicting. Then you have unsupervised learning. Unsupervised learning is a bit different. You don't have an answer. You just give an unsupervised learning algorithm your data and you say, find the pattern here. An example of that could be if you have lots of customer purchase data or sales data, and you feed it into an unsupervised learning algorithm, and what you get out is customer segments, because the algorithm manages to find the links between customers based on their purchase histories. And then you have the sexy one that everyone's really, really into right now, reinforcement learning. This is like the Google DeepMind stuff, the game playing, where you have basically an algorithm that adjusts its strategy all the time based on feedback from its environment. And this is really, really cool. Reinforcement learning is really cool. It's actually worth its own talk, so I'm not going to go into it any more detail. I'm actually going to focus on simple machine learning algorithms today, very, very simple ones. I'm going to give you an example of regression, which is basically predicting a continuous value or a house price. Classification, which is basically separating things into different groups. And clustering. And clustering is unsupervised, so that's like the customer segmenting example I gave you just now. And these are the algorithm types I'm going to look at. And for any of you who have any mathematical background, that you're probably thinking, Jesus, this is simple stuff. This is like high school stuff. And yeah, it is. Data science doesn't have to be about really complicated maths. Often when you're getting started with new data sets, you end up using the simple algorithms to try and understand what's going on. But the important thing here is understanding how the algorithms work. So let's start with linear regression. Linear regression is so simple, many people don't classify it as machine learning, but it is. Linear regression, I have an example here on the screen. I have a data set, and basically it's the size of houses and the price they sold for. So based on this information, I want to make a predictive model that tells me how much I'll get for a house sale based on the size of the house. So the good thing about this is it's basically two dimensions, so it's easy to visualize. So I have my features, which is the input data, and the label, or the value that I want to predict. And because this is two-dimensional data, I can plot it very, very easily. And applying a linear regression algorithm is basically doing this, drawing a line through the data, and I'll explain how that line is drawn in just a minute. Now, this line tells us lots of things. This is the actual model, and it tells us, you can call it a trend line as well, it tells us, it allows us to predict new house prices. So basically, using this line, we can say, based on a house being 5,000 square meters, we think it will sell for about 1.5 million based on historical data. Very, very simple. And it's linear regression, that's why it's a straight line. And the model isn't very good. This model's pretty crap because, well, you see this deviation here. You know, some of the training data is actually quite a long way from the resulting trend line. The reason for that is because this model is really simplistic. You don't predict house prices just based on the size, right? You predict house prices on, you know, how many bedrooms does it have? Does it have a garage? Where is it? You know, does it have a garden? Does it have a pool? All that kind of good stuff. This is a very simplistic model. And deviations like that can tell you if your model maybe is too simplistic. But how do you draw that line? How do you draw that trend line? Well, often you use something called ordinary least squares. And ordinary least squares is really quite simple. Basically, you have all your data points, and you have this red line in the middle. This is a trend line that the model is trying to fit. And what we do, or what ordinary least squares does, is it measures the distance between your training data and the average, or your trend line. And those distances are squared and added together to be a value called the sum of squared error. And basically what linear regression or ordinary least squares is trying to do is reduce the sum of squared error by moving that trend line up and down. And if you have outliers or bad data, bad outliers are things like noise in your data or one-offs, things that you don't really want to use in your training data. Outliers can drag your trend line away from where it should be. So that's one of the risks with things like linear regression and ordinary least squares. But, you know, linear regression is really, really simple and easy to understand. But once you start getting above 2 dimensions, it starts getting a bit tricky to visualize. Or once you get above 3 dimensions, it gets tricky to visualize. So the next type of machine learning algorithm I'm going to talk about for classification is decision trees. Anybody code here for a living? Coders? Lift your hand. Yeah, lots of coders. Just out of interest, how much middle management is there here today? A few, yeah. Solidarity brothers. Right, so decision trees are basically what we do when we code, right? Decision trees are basically if, then, else. That's what a decision tree is. But of course, with machine learning, we're allowing the algorithm to build its own decision tree. So basically what decision trees do is calculate the best split. That's what they do. They find the best split, the best feature to split your groups on. And I have a very simple example here. Imagine that there's a recruiting company in England that phones people up in Norway and tries to get them into jobs. This is a problem we have in Norway. And they've contacted me and said, we want a predictive model to tell us who should we give pay rises to next year based on what we did last year. Fine. So we have our data here. We have our features, placements. That means did they place a person in a job? Complaints. How many complaints did they get back because they ring up all the time? Have these recruitment consultants lived in Norway? Those are our features. And then we have a pay rise, yes or no. So it's 2 groups. We're trying to classify our data into 2 groups. So what decision trees do is try and find the feature that best splits our data into 2 groups. So if we looked at lived in Norway, it doesn't really split into 2 groups because we have people who got a pay rise on both sides. The same with complaints. We have people, you know, on both sides who got a pay rise and didn't get a pay rise. But if we look at placements, then we see that everybody who made a placement got a pay rise. And this is the feature that our decision tree will then split the data upon, resulting in, you know, basically a decision tree that says, okay, if somebody got placements, give them a pay rise. What happens if you have bad data? What happens if you have data which says that everybody who gets a complaint should get a pay rise? And this is one of the dangers of machine learning, because machine learning has no ethics. It doesn't really think about what it's processing. It just processes it. So if you put bad data into machine learning algorithms, you're going to get very bad models out. And you end up getting a bunch of recruitment consultants from England who get paid for getting complaints, which is basically how they work in reality. So if we go on to more complicated decision trees, because it's not always possible to split your data based on one feature. And then you have to do something called recursive partitioning. And here I have a very known data set, which is, should Mark play golf today, based on the outlook, the temperature, the humidity, and the wind. Those are 4 features. And there isn't one feature here that splits play into yes and no. So what happens is the decision tree first finds the feature that best splits the data. And we find that outlook, every overcast outlook record has play golf. So we start with that. And then we look at all the records where the outlook is sunny, and we try and find what splits the data there. And we find that humidity does it. And then we look at rainy outlook, what best splits the data there? Wind. And we end up with our decision tree. Very, very simple. And you see here that the temperature feature is being completely ignored. So that's decision trees. Really simple. Good for visualization. And they are prone to overfitting, and I'm going to explain a little bit about that in the next section, or the final section of this talk. Final machine learning algorithm I'm going to look at is K-means clustering, which I really like, actually, because I just think it's cool. K-means clustering is about finding groups of data, okay? And I've created a little test set here, 150 data points, plotted in 2 dimensions. And K-means clustering is going to try and group these, or find the groups in this data. Anybody want to take a guess at how many groups there are in this data? 3, right? It's obvious, right? And we have billions of years of evolution that help us make that decision, and a lifetime of experience. One of the things we do naturally or intuitively is find groups. But imagine, well, don't imagine your computer, but a computer will only have numbers. They won't have any visual grouping. They'll just have a bunch of numbers. They have to calculate this mathematically. So in K-means clustering, K is the amount of clusters the algorithm is going to find. And K needs to be a meaningful value. It needs to be just right, just like Goldilocks porridge, if you know that story. It can't be too many clusters or too few clusters. But how do we calculate K? That in itself requires some kind of mathematical calculation. And one way of calculating K, again, is the sum of squared errors. Now, sum of squared errors is what I showed you before when we were talking about linear regression. So in this case, what happens is we measure the distance that each data point has to the center of its cluster. We square them, and then we add them together to be the sum of squared error. And that sum of squared error is quite useful because we can plot it. And it's just like the linear regression example I showed you earlier on. So what you can do is you can actually calculate different amounts of clusters for your data set and see the sum of squared errors for each one, which I've done here. So I've made a simple scree plot, which shows us for different amounts of clusters applied to my data set, what was the sum of squared error. And what I'm actually looking for, I'm looking for the elbow of the plot, which here is 3. So, here mathematics is backing up what you said, that we have 3 clusters in this data. Now, there's different ways. This is a visual way of calculating K-means, but you can also use something like the silhouette coefficient if you want to do things automatically, but this is a nice one to visualize. So, okay, how do we apply it? How does K-means clustering work? Now we know we want to find 3 clusters. How does it work? Well, first thing that K-means clustering does is it applies 3 centroids, or 3 centers, to my data completely randomly. The next thing it does is it allocates cluster membership based on nearest centroid. These red dots are the centroids. So we see all the yellow guys here. They're the closest to that top red dot, and so on and so forth. But now our centers are no longer in the center of their cluster, so we have to move them to the center of the cluster. But now we have to recalculate our cluster membership, and so on and so forth. And after 6 iterations, we have a settled model. The centroids and clusters are stabilized, and we're good to go. And that's basically K-means clustering. Very, very simple. K-means clustering is very powerful and very quick. So you can actually use it for your exploratory data analysis. The main down point of K-means clustering is it uses a Euclidean distance to work out cluster membership. So it assumes that your cluster's around. But it's still a very good thing to have in your toolbox. So now we're in the end of the second part of the talk. The key takeaways are that there are 3 main types of machine learning. You have supervised learning, unsupervised, and reinforcement learning. Machine learning is more than neural networks and deep learning. This is what I've tried to show you here. There are some relatively simple machine learning algorithms out there which you can have in your toolbox, which mean that you don't have to go straight to TensorFlow. And I really do recommend, if you are starting upon your data science journey, you don't just download TensorFlow and begin there. It is actually better to start with the more simple algorithms to understand your data before you break out the big guns. A successful machine learning model needs to find a balance between overfitting and underfitting, just right. And that balance is a sliding scale, depending on your training data, depending on your use case. So the balance between underfitting and overfitting is something you have to evaluate during your project. And machine learning algorithms are just tools. Most of them are already implemented. So to really get value out of them, you have to understand how they work and how you can configure them. Right, so now we're going to go over to a little practical example of data science. And I'm going to show you some code. I'm not going to do any live coding, don't worry. But I'm going to go through an actual data science project, or an example of a data science project. And what I'm going to do is I'm going to build a decision tree. that tells me how likely it was that somebody would survive the Titanic disaster. Now, the reason I'm using Titanic is there's two reasons for that. One is it's a very known use case in data science, and number two, almost everybody has seen the film. If you haven't seen the film, to sum it up in just a few words, a load of people get on a boat hits an iceberg, all the poor people, including Leonardo DiCaprio, die, and all the rich people, including Kate Winslet, survive. That's it. The actual film is 3 hours long, which is actually longer than it took for the ship to sink. Imagine that. But anyway, so my hypothesis is that you can predict survivability on the Titanic based on 3 variables: the age of the passenger, the gender of the passenger, and the class of ticket. And my data set looks like this. Basically, I have all this great data here. Most of it I'm not really paying attention to. I'm really only interested in, did they survive or die? The class they traveled in, from first to third class. The gender. This is back in the early 1900s. So this is before we got all woke and we had they as well. But now in that time they just had male and female as gender. And we have the age in years, which is a continuous variable. The tools I'm used for this are actually scikit-learn. Anybody use scikit-learn? Oh, yeah. Awesome. Scikit-learn is basically a Python distribution which contains lots of implemented machine learning algorithms, and also lots of other good stuff. And I'm displaying my code in a Jupyter notebook. Now, for those of you who can Python, who know Python, my Python code isn't always the best, so please don't cry and don't throw anything at me. I know I need to get better. Right, so let's go over to my Jupyter notebook then. Let's see if we can bring that up. Now, for those of you who have never seen a Jupyter notebook before, it's just basically, and I'm going to zoom into this, don't worry. For those who've never seen one of these before, basically you write code and you get your results in the notebook. And it's a great way of sharing your data science analyses with other people. So that's the main reason you use Jupyter notebooks. And we can quickly scroll through it. As I said, I'm going to zoom into the relevant bits in a minute, but you can quickly scroll through it and you can see there's visualizations and all kinds of good stuff there. But there's a nice little plug-in for Jupyter Notebooks, which is called Rise, which gives you the ability to actually visualize your stuff in a kind of PowerPointy type manner, which I'm using here. So the first thing I do with my data, I have my data. First thing I'm going to do is I'm going to import it using something called Pandas. And we can zoom into our data here. We can see all the information we have here. We can see, for example, there are some ages missing, and I'm going to come back to that in a minute. We see that we have the full names, and there's lots of good data here. So, okay, we have our data, but we see that some of the ages are missing. That's actually quite a worry for me. So the next thing I'm going to do is I'm actually going to do a simple describe on my data. And what I'm doing here is I'm allowing Pandas to perform some simple statistic analysis on my data set. What this tells me is that we have 891 records in our data set, but we only have 714 ages. So we're missing ages for about 177 of our passengers in our data set, which is a problem, because these can be outliers, which, missing ages can actually mess up our machine learning model. So I need to do something about this. I can either remove this data, which would possibly mean that I remove a quarter of my training data, or I need to find some way of solving that. Another thing that I get from this is if I look at the mean value of survived is set to 1 if you survived or 0 if you died. So if I look at the mean value of survived, I can guess that like 38% of the people in my data set actually survived the disaster. So I'm going to do some feature engineering. Now, feature engineering is what data scientists use a lot of time doing. Feature engineering is basically enhancing the data, finding new features from what you have. And as I mentioned before, I don't have the age values for 177 records, so I need to find them. And what I've decided to do, I'm going to be quite lazy. I'm going to do this in the simplest way possible. I'm going to work out the honorific for each passenger, extract that from the name, and I'm going to calculate the median age for each honorific, and then use that to replace the missing age values. So pretty simple stuff. So the first thing I need to do is I need to extract the honorifics, which I do here. Now I have a new column called honorific. Luckily, the honorific is at the same point in every name. So this is data that's been processed a certain amount. And then I'm going to see how many honorifics I have. And what we can see, if I can zoom in here, we can see that we have quite a lot of misters on the boat. Then we see lots of potential outliers, like or unique values, like the Countess, very nice. Don, which is I think Italian for Sir. Ms, Jonquier, Madame, Mademoiselle, which is French for Miss and Mrs. So there's lots of different ones here, but what I'm going to do is I actually want to normalize those a little bit and try and simplify our honorific map if I can. So what I do is I create a simple map here, and what I'm doing is I'm converting the existing honorifics over to some other values. So for example, captain, colonel, doctor, major, reverend, we're going to put them all together into servicemen. Because when I think of these things, captain, colonel, in the early 1900s, they're kind of like a middle-aged man, moustache, drinks a lot of brandy, walks around like this, So that's what I think of them. So I'm just going to group them all together. Mademoiselle, that's Miss, of course. Madame is Mrs. The Countess becomes lady, and so on and so forth. So what I do is I end up washing my honorifics, and I end up with less honorifics. So what I do next is I actually create a box plot, which shows me my new set of honorifics, which are lady, master, miss, Mr., Mrs., serviceman, and sir. And I've basically visualized the age distribution for each honorific using a box plot. And what's interesting here is actually, if you look at the top here, if you see where I've got the mouse here, you see some outliers here on the ages, but I'm not going to worry about those now. I'm really worried about this green line here, which is the median age for each honorific. And that is the value that I'm going to use to replace the missing ages. So all of those ladies with a missing age will end up with an age of 41 and so on and so forth. Master, around about 7. Miss, around about 21. Mr. 30. Mrs. 35. Serviceman 50, which is about right. I said servicemen, they walk around and walk. So that's about right. And then we have Sir, which is about 40. So that's my feature engineering for the ages. Now I've filled up all my ages, or that's what I do in this section here. And then what I'm going to do is I'm just going to I'm going to fix the gender or the sex categorical variable, because that at the moment is actually set to male or female. Machine learning prefers numbers, thank you very much. So what I'm going to do is I'm just going to convert it. So basically male will become 0 and female will become 1. So now I've done all the feature analysis or engineering. Now I want to see, does my data actually reflect my hypothesis? I've not got to the machine learning bit yet. And I just want to do some simple plots to see, does the data reflect my hypotheses? And what we have here is a simple plot of, let me see, class versus survivability. So first class, second class, third class. So orange or brown means you survived. Blue means you died. So if you're in first class, your chances were relatively okay. In second classes, your chances were 50-50. In third class, that was like, you were pretty much, stuck. What this also shows is the distribution of my data. It shows that I had a lot more people in my data set that were in first class than in first. But anyway, what we can see here is survivability is definitely related to class. What about gender? Here we go. Here's one. Now, in today's society, we are very focused on equal opportunities and fairness, 50-50. But in those days of the Titanic, it was women and children first. So men were basically turned away from the boat. So what we can see here is that basically if the gender of 0 is men, and that shows a very high death rate. And the women, good for you sisters, they had a really good survival rate. So we can see that, again, survivability is related to gender. But then we come to age. Age is a bit tricky, because age is a continuous value. It's not like binary, right? So you need to do something with it to make it plottable. So what I'm doing is I'm basically splitting my data and saying that everybody who has an age of 14 or under is a child, everybody over 14 is an adult. And here we see that age isn't necessarily alone a very good predictor of survivability. And the reason for this, I think, is because a child's survivability was very much based on who they were traveling with. If they were traveling with a parent in first class, then things were good. So I think age has a high correlation, or has a lot to do with, or the survivability of children has a lot to do with both the class they were traveling in and the gender of the person they were traveling with. So it starts to get quite complicated. So I'm going to key page because I think it does have something to do with survivability or not. So I have all these features I want to get rid of, so I get rid of all the rubbish. So now I've just got these features. This simple feature, I've got class, sex and age, and the survivability. So then I start building my machine learning model. Finally, I've got to the point where I build my machine learning model. I've gone through the hypothesis, I've gathered my data, I've gone through the exploratory data analysis, and now I'm at the point where I can actually start building my model. And I split my data up. I also split my data into training and testing sets. Why do I do this? Well, anybody who works with machine learning knows that you do not test your model with the same data you trained it with, because you want your model to generalize, and you want to show it data it's never seen before when you're testing it to see how well it works with that. So I'm putting aside 25% of my data for testing. And now, ladies and gentlemen, the machine learning. There we go. That was it. Scikit-learn has a bunch of classifiers and implemented machine learning methods and algorithms, and decision tree classifier is one of them. So I'm basically feeding it my features training set and my labels training set and saying find a correlation between these. And all of these values down here, these are hyperparameters which I've just left as they are. So I didn't tweak any of the model's hyperparameters. So let's score it with our testing set, and we see we get 75%. 75% accuracy. Not bad for first go. And because we're building a decision tree, we can actually visualize it. Ooh, there we go. There's our decision tree. I think maybe I need to come out of here and show you the decision tree properly and how big it is. There's a decision tree. Now, I would argue that's a bit deep. Maybe a bit overcomplicated. It's definitely overfitted. What we've allowed to happen here, we've allowed the decision tree to just build and build and build. We haven't said to it, we want you to stop at any point. And because of this, the decision tree has become very specialized to our training data. So I have a hypothesis that if I reduce the size of the tree, I can actually get better results. So let's do that. Let's just pick a number, 3. 3 is a good number. The amount of features we have, we'll say that our tree can only be 3 nodes deep. And we'll train it. And we see here I've changed this hyperparameter here, max left to 3, but all the other ones are left the same. And the results are, 80%. So I got a 5% improvement just by pruning the tree. And this is important because here we are talking about understanding how the machine learning algorithm works, but also understanding how to tune it to get better results. And you can even visualize this tree, which, with a little bit of work, this actually could be presented to middle management like me, we'd understand it. So we see here that, it's not just about running machine learning algorithms willy-nilly and just hoping they work. There's a lot to do with understanding how they work and understanding how you can tune them to get the best results. Okay, let me just go back to my PowerPoint. Right, so some key takeaways from that. So scikit-learn and Jupyter Notebooks are really a great way for messing around with data science. They're free. One good way of getting hold of them is downloading what is called the Anaconda distribution. And that's basically a pre-packaged distribution of loads of different data science tools. And by doing that, you don't have to worry about different dependencies. So when you start dealing with libraries that have different dependencies, and you can use the whole day on that. So by using Anaconda's distribution, you can really save some time. Feature engineering is a vital skill for data scientists. If you are middle management and you are going to hire a data scientist, one of the things you should be asking them about is feature engineering. Running algorithms in themselves, often these algorithms are already written by somebody else. You're just pressing a button and running them. So, feature engineering, understanding how the data works and how to get the best out of it is really an underrated skill in data science. Domain knowledge is key. You have to understand the domain. The Titanic example was relatively simple to go through because you all know the domain from before. But if you didn't know the domain, then it would have taken a lot more time to explain it. So understanding the domain is really, really important to get to understand, for example, that women and children first. That's what my entire hypothesis was built on. And to know that, I needed to read up at the domain. Split your data into test and training sets. Don't test your model with the same data you trained it with, because as soon as your model sees new data, it might fail. That's one of the things that often happens that people forget to do. Split their test and training data sets. And And finally, tweaking hyperparameters, like the depth of a tree, all that kind of stuff, can really make a difference. But you need to understand why your model, when you tweak these hyperparameters, why your model gives you better or worse results. So, I think that was it. I would just like to say to you all, thank you for coming. I hope you enjoyed the talk. I'm going to be doing another talk in here at 11:20, I think. So feel free to turn up to that. Other than that, enjoy the conference and have a fantastic 2 days. Thank you very much.